following is a presentation of Video Lab Report Number 1, Physics 2211, Modern Physics with Dr. Greco. This experiment primarily focuses on applying Newton's second law to an object which travels at a constant velocity. Content which will be covered in this presentation includes basic information regarding the experiment, defining the system and the surroundings, physical modeling of Newton's second law, computational modeling of Newton's second law, predicting the motion of an object traveling at constant velocity via statistical data, acknowledging error in the physical model, and last, concluding remarks. The object's motion which is being analyzed in this experiment is a standard size lacrosse ball, of which the mass is equal to 0.140 kilograms. During the physical modeling, the ball is traveling at a calculated constant velocity of 0.94 meters per second in the negative x direction. This was determined by using the calculation delta v is equal to delta r, the change in the object's position, divided by delta t, the time interval between the two measured positions. It should be noted that delta v is equal to the ball's final velocity because there is no net force acting on the lacrosse ball. This is according to Newton's second law. This video was calibrated by using the known measured height of the box of Pop-Tarts to be equal to 0.135 meters. Finally, the total time frame of the ball's change in position lasts for 2.1 seconds, during which there are 117 frames filmed at a rate of 30 frames per second. In this physical model of the lacrosse ball traveling at a constant velocity, the lacrosse ball itself acts as the system. In the experiment, the ball is defined as the system because it is the object's motion and properties which are being observed. Keeping this in mind, the surroundings of this experiment are all other objects and forces which interact with the system present in the captured video frames. In the physical model shown on Tracker, one will first see the raw video of the lacrosse ball rolling across the screen from right to left. In case anyone is curious, the box of Pop-Tarts is present because it served as the object whose measurement would be used to calibrate the video. Now as I activate the X and Y axis, the calibration stick, and the track control diamonds of the object in motion, one will see the path upon which the ball travels. Likewise, one will notice the linear trail of yellow diamonds which is left behind by the ball as it rolls across the screen for 2.1 seconds. As it was previously mentioned, the ball rolls at a constant velocity for 0.94 meters per second in the negative x direction, as no external forces are exerted upon the rolling ball. Therefore, this object moving at a uniform velocity satisfies Newton's second law. The computational model was created by first editing the prescribed code in feet idle. Sections which were edited include the lacrosse ball's mass, the position and velocity vectors of the lacrosse ball, the total time elapsed, the F-net acting on the ball, the addition of Newton's second law, and finally the adjustment of the position vector. The ball and stick model replicates the ball's position and velocity as it travels from right to left in the negative x direction. The corresponding graph shown to the lower left then indicates the position of the lacrosse ball as a function of time. Together, these two components represent the computational model of the physical modeling of the object in motion. After taking the time and position data from the Tracker application and considering the computational model's prediction, one can see both the numerical and the graphical representation of the object's predicted position. It should be noted that the entire data table cannot be included as an image because it was over 200 cells tall within Google Sheets. However, the entire model versus experiment chart was included because it could be scaled to size. As one studies the graphical model of the lacrosse ball's position, we'll see a slight derivation between the ball's actual position, the blue dots, and the projected position, the solid red line, as time continues. This indicates that the experimental data has an extremely high correlation with the projected position of the system which is moving at a constant velocity. Although the error present in this experiment did not change the final results, it should still be acknowledged. If one looks closely at the x-axis present in the Tracker video clip, one will see that the axis is not 100% horizontal with the shelf which the ball rolls on. This is indicated by the two arrows showing the slight difference in height between the x-axis and the base of the shelf. According to Newton's second law and the calculated results of this experiment, it can be said that the lacrosse ball, the system, is traveling at a constant velocity as it moves in the negative x direction from right to left across the screen. This constant velocity, as previously calculated, is equal to 0.94 meters per second in the negative x direction. Because there is a net force of 0 acting on the ball, the lacrosse ball travels with a constant velocity. It can also be concluded that the predicted position of the ball almost exactly corresponds with the actual position of the lacrosse ball according to Tracker's data. In addition, the aforementioned error in the orientation of the axis did not largely affect the experiment, and as a result allows this experiment to serve as an example of all objects which travel in one direction at a uniform velocity. What if? If the axes were flipped so that the lacrosse ball was rolling from left to right across the screen, the ball would proceed in the positive x direction instead. In addition, the model versus experiment chart would have a positive slope in both the x and y directions. What does it mean? The initial inertia-based resting force of the lacrosse ball was overcome in order to get the ball rolling. When in motion, the initial acceleration of the lacrosse ball was counteracted by the opposing drag force. As a result, there was zero net force acting on the ball traveling at a constant velocity.